Hello friends, welcome to Bindu Dhadwal Chemistry Lessons. The topic for today is chemical reactivity of group 15 elements. Nitrogen has a unique tendency to form p-pi multiple bonds with itself and with other elements having small size and high electronegativity, for example carbon and oxygen. However, the heavier elements of the group do not form p-pi bonds because their atomic orbitals are so large and diffused that they cannot have effective overlapping. This results in anomalous nature of nitrogen reactivity towards hydrogen. Hydrides are respectively named as ammonia for nitrogen, phosphine, arsine, stibine and bismuthine. Nitrogen also forms hydrazine. Phosphorus forms diphosphine, P2H4, and arsenic forms diarsine, As2H4. There is another hydride of nitrogen, hydrogen azide, also known as hydrazoic acid. Preparation of hydrolysis. So metal nitride or metal phosphide or arsenide is reacted with water and ammonia, phosphine, arsine hydrides are formed. By reduction of trichlorides also we can obtain the hydrides. For example, ECl3 when reduced with lithium aluminium hydride will form EH3 plus lithium chloride plus aluminium hydride, where EH3 is the hydride of group 15 element. The structure, all are covalent and have pyramidal structure. Nitrogen is engaged in sp3 hybridization. Of the 4 sp3 hybrid orbitals, one is occupied by lone pair of electrons and the 3 are occupied by shared pairs between nitrogen and hydrogen. Bond angle decreases down the group. For ammonia it's 107 degree, but for phosphine 93.6, arsine further less 91.8, stibine 91.3 and bismuthine is 90 degree. Why the bond angle decreases down the group? It is because the central atom is surrounded by 4 electron pairs, and the atom, in case of ammonia, the nitrogen atom is very small. It has high electron density, and these lone pair and bond pairs are present close together to each other as well as to the central atom. So this results in repulsion, because of which this bond angle is higher. But as we go down the group, the size of the atom increases, because of which the bond pairs, they start moving away from the central atom. Repulsion decreases, so the bond angle also decreases. So you can see more repulsion, bond angle is large in ammonia, and less repulsion, bond angle is less. Characteristics of hydrides. Basic strength. So all the hydrides have one lone pair of electron in their central atom. Nitrogen atom has smallest size. Lone pair is concentrated on a small region and electron density is maximum, so electron releasing tendency is maximum, so it's most basic. But as we go down, size increases, electron density decreases, so basic character decreases. For thermal stability, the stability decreases in the order. Ammonia is most stable. As we go down, the stability decreases because bond increases and bond dissociation enthalpy decreases. Reducing character also increases down the group. Reducing character increases down the group because stability decreases down the group. A less stable bond is more easier to break. It can release hydrogen, which can reduce substances. Next property is boiling and melting points. So boiling point of ammonia is higher than that of phosphine. This is because of hydrogen bonding. The electronegativity of nitrogen is maximum 3, whereas as we go down, the electronegativity decreases. So because electronegativity difference is higher in case of ammonia between nitrogen and hydrogen atom, the bond is polar and nitrogen can form hydrogen bonds. Hydrogen of ammonia can form hydrogen bonds with nitrogen of next ammonia molecule. Similarly, this nitrogen can form hydrogen bond with hydrogen of adjacent ammonia molecule. So because of presence of hydrogen bonds, the boiling and melting points are higher in ammonia. Phosphine has lesser melting and boiling point. But down the group, arsine will have higher melting and boiling point than phosphine because it's of bigger size and van der Waals force attraction increases with the size of the atom. Stibine is still bigger, so the boiling point will be more. Solubility. Ammonia forms hydrogen bonding with water molecules, so it's highly soluble. Phosphine and other hydrides do not form hydrogen bond with water, so they are insoluble in water. Reactivity towards oxygen. This is the second property. First was formation of hydrides. This is formation of oxides. So elements of group 15 form two types of oxides, trioxides and pentoxides. However, nitrogen forms a number of oxides. You can see for nitrogen there are a number of oxides like varying from oxidation state 1 plus 1 to plus 5. We have for nitrogen nitrous oxide, nitric oxide, dinitrogen trioxide, dinitrogen tetroxide and dinitrogen pentaoxide. For phosphorus, phosphorus trioxide, tetroxide and pentoxide are there. For arsenic only 2 oxides, tri and penta, antimony also 2 and bismuth also 2 oxides. The acidic character decreases as we go down the group. Acidic character of oxides decreases as we go down the group. Also, the oxides in higher oxidation state are more acidic than oxides in lower oxidation state. So, nitrogen pentaoxide is more acidic than nitrogen tetraoxide. Similarly, phosphorus pentoxide is more acidic than phosphorus tetraoxide. Acidic character of group 15 decreases down the group. Nitrogen trioxide is more acidic than phosphorus trioxide. Of these, arsenic oxide and antimony oxides are amphoteric and bismuth oxide is weakly basic. Nitrous oxide and nitric oxide are neutral, whereas higher oxidation states the acidity goes on increasing as we move to higher oxidation state. Reactivity towards halogens. The elements of group 15 form two types of halides, trihalides and pentahalides. Nitrogen, phosphorus, arsenic, antimony, bismuth all form trihalides with fluorine, chlorine, bromine and iodine. The trihalides are pyramidal in nature. They undergo sp3 hybridization. Of the 4 sp3 hybrid orbitals, one is occupied by a lone pair of electron. The bond angle increases as the size of halogen atom increases. The trihalides are generally covalent. Ionic character increases down the group. The trihalides of nitrogen exist as Lewis bases, presence of lone pair of electrons on nitrogen atom. As d orbitals are not there, so tendency to accept electron is not there, and as there are lone pair of electrons, they can donate, so they act as Lewis bases. NF3 has a little tendency to donate a pair of electrons. It is a very weak Lewis base. This is because fluorine is highly electronegative and it attracts the shared pair of electrons towards itself. As a result, there is a partial positive charge on the nitrogen atom, which makes it weakly basic. So basicity will increase as we move from NF3 to Ni3. Tendency of trihalides to act as Lewis base decreases from nitrogen to bismuth for a given halide. The trihalides of phosphorus, arsenic, antimony, they act as Lewis acids and combine with Lewis bases. The vacant d orbitals in these will accept electrons from ligands to form pentahalides. So PF3 accepts electrons from fluorine to form PF5, antimony forms SPF5, SbCl3 can take chloride ions to form SbCl5, 2 negative, and so on. Lewis acid strength decreases, PCl3 is more than ESCl3 than SbCl3. PF3 acts as a better Lewis acid than PCl3, than PBr3, than PI3. Out of all the trihalides of nitrogen are the least stable. Only NF3 is stable, NCl3 is explosive, and tribromides or triiodides only exist as ammoniates, which two are unstable. NBr3 may also explode at 173 Kelvin. NF3 is stable because the size of nitrogen and fluorine are of almost equal dimensions. Nitrogen radius is 75 picometer, fluorine is 72, so there is a strong bond. Exothermic compound is formed. It does not hydrolyze with water because there are no d orbitals, dilute acids or alkalis. So all these are unstable. The halides, trihalides of nitrogen, trichloride, bromides, iodides are unstable. In the dry state, triiodide ammoniate decomposes to give nitrogen iodine and ammonium iodide. Trihalide, nitrogen trichloride with water, ammonia and hypochlorous acid is formed. All are hydrolyzed, but products are different. In case of NCl3, hypochlorous acid is formed. In case of PCl3, this orthophosphorus acid and HCl is formed. In case of arsenic trichloride, arsenic oxide and HCl is formed. Antimony and bismuth trichlorides are only partially hydrolyzed to give antimony oxychloride and bismuth oxychloride. So group 15 also form pentahalides. Only phosphorus, arsenic, antimony form stable pentahalides. Nitrogen does not form because of absence of d orbitals. In case of bismuth, the inert pair effect comes into play. Even though it forms pentahalide, they are not stable, they are less stable. Then the hybridization that it undergoes is sp3d, and the structure is trigonal bipyramidal. In the structure, you see that all the 5 halogens are not showing equivalent positions. 3 are equatorial positions, 2 are axial positions. The bond angle is different. For equatorial position, bond angle is 120 degree, whereas for axial it's only 90 degrees. So more repulsion makes these 2 bonds longer, because of which they can be easily broken. So PCl5, it acts as a very good halogenating agent. PF5 is molecular. PCl5 exists as crystalline solid in the solid state, and these elements can act as Lewis acids because they can accept pair of electrons to form octahedral complexes. For example, EX5 from sp3 hybridization changes to sp3d2 octahedral complex when it accepts a halide ion. As we go down the group, the stability of +5 oxidation state decreases due to inert pair effect. Except BiF5, other halides, pentahalides of bismuth are not known. As size of the halogen atom increases from fluorine to iodine, the strength of central element halogen bond decreases and steric hindrance increases. So pentabromides and pentaiodides are unstable. Pentahalides of group 15 are less in number than trihalides, and they can be prepared by reacting them with halogenating agents, reacting trihalides with halogenating agent. Reactivity towards metals. So elements of group 15, when they react with metals, they form binary compounds. For example, nitrides, phosphides, arsenides, antimonides, and bismuthides. Anomalous behavior of nitrogen is due to small size, high ionization enthalpy, and absence of d orbitals in the valence shell. Anomalous behavior means that the properties of nitrogen are different from rest of the members of the family. How nitrogen differ from other family members? It's a gas. Other members are solid. Nitrogen does not show +5 oxidation state. Other elements show. Nitrogen can form p-pi bonds and exist as N2 molecules, while other members form single bonds. Due to absence of d orbitals in the valence shell, nitrogen cannot form d-pi-p-pi bonds, and therefore compounds of the type R3N double bond O and are not known. However, phosphorus and arsenic form compounds such as R3P double bond O and R3P double bond CH2 containing d-pi-p-pi bonds. Hydrides of nitrogen are more basic than hydrides of other members. Nitrogen does not form any complexes, whereas other elements form complexes. Nitrogen can form hydrogen bonds in its compounds. Nitrogen can form a variety of oxides, whereas others form only trioxides and pentaoxides. And the nitrogen halides are unstable, whereas trihalides of other elements are stable.